Okay, so we are live. This is the Hamilton Meetup. We have these both for the for people to sort of have a nice engagement with the Hamilton community, and then a lot of people actually watch it on YouTube later. I think a lot of people will sign up for the Meetup and then log it on YouTube later. So any questions you have, any sort of contributions are really valuable. Cool. So let's get started with the Hamilton Meetup. Is this the right one? Let me just see. I think I copied the. Yep. So this is the December 2024 Meetup. I was the wrong one. All right. Cool. So yeah, what is Hamilton? You guys will know it. Hamilton helps data science engineers define testable, modular, self-documented data flows that include lineage and metadata, run on scales over Python does. If anybody wants to introduce their name and what they're using Hamilton for, I did this earlier, but I'm Elijah. I'm one of the co-creators. Yeah, really using Hamilton for pretty much everything I can find, most personal data projects. And I'm looking for user feedback, trying to understand sort of the direction to go from the community. The community members drive everything we do. So it's super exciting. All right, anybody else want to share what they're using Hamilton for? As Jernej, you'll introduce yourself in a bit, so we can. Cool. All right. Yeah, so on the agenda today, first, community spotlight from Jernej. Next, we'll talk about some news. News is in quotes. It's really just new features. And then open mic. Feel free to talk about whatever you want. Usually this has lasted an hour and a half. I think this one might be a slightly shorter one. Holidays and everything. So yeah, let's talk about Jernej Frank. Let's give this over to Jernej, who's been a prolific contributor, a prolific user, and has gotten deeper into Hamilton than most people I've ever seen. So there are some, and the really cool thing is he's going to be talking about sort of a core thing we designed now years ago that has been an abstraction that's kind of proven its usefulness again and again and again, and has some limitations. He's really dug into it in multiple different ways and probably understands it as well, if not better than myself who created it. So he's going to be talking about what he's learned, his experience contributing, and a few different sort of pointers along the way. So Jernej, feel free to share your screen if you can.
You have to allow me.
Let me just settings.
No pressure. I'll let you introduce me.
I added you as co-host, so you should be able to share now.
Thanks, Jernej.
Awesome. All right. Let me just. It still says my screen is not allowed to share.
So you said you added Jernej as a co-host.
I had it for like a brief moment, but then it disappeared again.
Add as co-presenter. Let's try that.
Oh, I think it's Elijah. You will have to remove your sharing first.
Oh yeah, I can do that. I added you as a co-presenter, Jernej, and I removed my sharing. So hopefully those two, one of those will solve it. Nope.
Nope. The icon is still. The only icon I cannot click is sharing screens.
All right. I'm gonna remove you as a co-host and add you again. Otherwise, I'll share my screen and advance because I have your slide.
Wait, I can do now.
I enabled everyone to share their screen, so let's just keep the safe.
Cool.
That's awesome. Can you all see the?
Yes.
And now you cannot.
It was there for a second, but we lost it.
I promise I develop better code than sharing screens.
Elijah's on mute too, so it's funny to see.
Okay, I'll just keep it in the PDF. Okay, awesome. Right, so my name is Jernej Frank. I've mostly been a scientist my whole life, and recently switched more to being more serious about software engineering. And just to give you a brief introduction, I got introduced to Hamilton as a user, working on a pipeline that converts models into production-grade deployment by quantizing them. And the pipeline was fairly short, but had a lot of moving pieces. And there were two major things that kind of were under development at that point. So Jerry was just bringing out his MLflow plugin, which was really helpful to me because we were saving the models in MLflow, and he was happy to add an additional thing to it. And then the way we were quantizing those models is basically by distributing them over multiple GPUs using Ray, and then Hamilton's telemetry tracking and Ray didn't really talk to each other at that point. So this was a blocker in my project, and I reached out to Elijah and Stefan and offered to help with this to make the telemetry tracking work. And this was then my first actual project in the community. And what I expected is that both of these things are adapters. They're somewhere on the outer layer of Hamilton, and I'll get some introduction of how to collaborate on open source projects and get some idea of how Hamilton functions under the hood, and fixing the thing that actually bothered me. What actually happened is that what I didn't realize is that even though both are adapters, they run straight through the driver execution framework, and that meant I actually was thrown into the very heart of Hamilton by Elijah from day one, and had to add a whole, had to understand how the lifecycle hooks work, which I'm not going to talk in this talk, but they're also fun. And then had to add my own lifecycle hook, refactor the Ray graph adapter from the legacy design to the new design, and actually did some surgery that at the execution level. All in all, very deep. I loved it just because I love going deep into things, and also Elijah and Stefan were there every step of the way, really guiding me. And this is how, after the PR closed, my first thing I did is basically message them, cool, can we do it again? And since then, what I did is mostly work on decorators. So this is the other side of Hamilton. The first part would be kind of on the execution side. This side is more on the how you actually create your pipelines. And I'll just take 3 steps back and first start with general introduction to Hamilton, and then I'll go more into decorators, because I think it's hard to understand why decorators are there if we don't have the general picture of it. So Hamilton really shines in making your experimentation clean. What usually happens is when you work with data is you don't really know where you're going. So you have a Jupyter notebook, for example, you add some things and then you keep changing them until you have a plot that you like, and then you email that plot. And for me, at least on a good day, the Jupyter notebook that I actually saved is the one that produces the plot. On a very good day, the cells in the Jupyter notebook actually execute in one order down. And I tried not having such a messy workflow with data. Did once actually refactor it. It took a long time. The person I sent my Jupyter notebook to it didn't do it. We were back to square one, and it was like, why are we even doing this? The other thing is version control. When do you commit? Do you commit every time you change the value? Do you commit like on a major piece? So it's not really easy to use software engineering principles when you're working with data until you meet Hamilton. And Hamilton does really provide this capability of breaking up your code and being able to track all your steps, and gives you the perfect tool for daily experimentation. How does Hamilton do this? The basic principle philosophy is very simple. every asset, every node in your pipeline is represented by a function, and then the functions are stitched together by the names and the data types. And this is the general essence of how Hamilton imported cleanness to your code. Now, having this restriction is really powerful because it really makes you disciplined. But on the other hand, it turns something that's very explicit also into a problem, because you run the trade-off of everything now needs to be very verbose in your code. So for everything you want to do, you have to write code for it. And it's not one line, but it's actually like functions. And just to illustrate this, let's just imagine a small fraction of a pipeline where, let's take, we need to do 2 calls to databases, one for the US market, one for Europe, and then you fetch 3 dates out of it, and you want to calculate the duration between the dates. And we want to do it in Hamilton and make everything explicit. So if you do this with the basic functionalities of Hamilton, the ones that I just presented, this looks very messy, because you have, for everything, you have to have your own function, your own node, and it's very hard to see what's happening. So this is the actual code that produces that DAG. So you see that here's the database calls. Then for every single node, you actually have to define a function that quite often do repeated things. And then at the end, you have to push in some if statements. And it's not hard to see how this explicitness, which is really good on one hand, also can harm code maintainability and readability. So there's a couple of things we can do already, still staying on the basic functionality. For one is we could use, for example, a helper function, which is not part of the DAG, but does exactly that it abstracts away some functionality, so that, for example, here that we convert all the date formats into the same format. And if we do that, the code already becomes much cleaner. When we use those helper functions, they're good, but when they reduce verbosity for us, but at the same time, they also reduce the explicit character. So we stop seeing things in the DAG. So we're back in the first part of the problem, that we're not able to track things, or at least not all of them. So here's the DAG, by the way, how it looks when you use a helper function. So it looks a lot cleaner, and you have a better idea. Just now, the problem is that you don't know exactly where things happen. Okay, so the question is, can we actually do better than just using helper functions? And this is, can we reduce verbosity and maintain the same level of explicitness, or even better explicitness than before? If you quickly count the nodes here, you would see that I have 12 nodes. The first DAG had 10 nodes, and the helper function had 8 nodes. Does this mean that we actually have to write 12 functions now to keep this level of explicitness and keep everything at the same level or even more verbose? The answer is no. And we can do this by moving logic that was originally within the nodes onto the level of the DAG. So before, we had one function was corresponding to one node. How about we make, on the user side, something that's not only a function, but a function with certain instructions how the node should behave. And these instructions get applied on the node level and actually do not result in a single node, but actually result in a whole subgraph. And this is the whole idea of using decorators. So Hamilton under the hood has certain decorators defined, and what the user actually does is he has his function, and then he adds these instructions on top of it, and they create all the DAG manipulations for them. For anybody who doesn't know, a decorator in Python is a function that modifies or extends an existing function. So it takes a function as an argument and returns a function. How Hamilton uses decorators is a bit untraditional, because the way Hamilton does it is actually it attaches instructions to the function itself. And this is critical because it decouples the creation of the DAG with what the user defines. And basically, the instructions don't get executed until later on when the DAG gets built together.
So you might be getting this soon, but how is this different from the standard way that Python uses decorators? I think it's kind of a fun point here. Or is the common way that people think about decorators?
Yeah, so commonly you would have, for example, a function would return a string, say hello. And then the decorator would say, I'll take this function and append a string after or before that function so that my new function returns hello or something before and hello. It would directly, maybe Thierry has like a better example on the top of his head.
Yeah, I think it's a interesting observation is that when you use decorators in Hamilton, you will need to have Hamilton installed because there's the Hamilton decorator in your code, but the function is still the same. It's not transformed the object. The function is still usable. Whereas if you use prefect and you add the task decorator, or you use DLT and you add the resource decorator, you're no longer getting a function. You're getting a DLT resource object or a prefect task object. And so these come with more burden to carry around. They're no longer just the function. They're a whole object from the framework. Whereas Hamilton returns the function with some things attached to it.
Yes, that's almost even another way, right? So the way that we would use it, as Jernej was saying, is we just mark it and use it later for a compilation step. The standard way to do it in like the Hello World decorators are you do something, some side effect or some manipulation of the result, right? And then the complicated way of doing it, which is how functools.lru cache works and how prefect and DLT both do it, is to turn it into an object, which might or might not have the callable and also probably looks different. So awesome. Sorry to interrupt you. I just think it's a really interesting point on decorators that I haven't seen people think about using it this way, but it's actually a very valid way to do it.
Yeah, I wasn't sure. Didn't know about DLT either, so that was a cool thing to learn. But yeah, watermarking is really cool because you delay execution, which is really important for Hamilton. So to see why this is important, let's go through a full cycle of how Hamilton builds a DAG. You start off with your module where you define your functions, you decorate them, and then you have the typical driver builder of the driver, where you provide the module and you provide something like a config file, for example. And then what Hamilton does is it takes this module, it crawls through the whole module, collects all the Python functions, and then at this step, it starts going through each of the Python functions and starts creating a subgraph for that Python function. And what happens in that step is basically it checks all the decorators that have been watermarked to that function. And then for each decorator, it basically calls all the instructions it's supposed to call. And then it applies them to the graph and then returns that subgraph instead of the function, and then combines all the subgraphs and validates it, and then you can execute it as a Hamilton DAG. Right. So there are 6 different graph operations in Hamilton that get executed in the same order that are listed here. And this is important because each operation, like some operations cannot precede others, basically, right? So if you start in the beginning, and I can just jump through them because the next slides are basically going through all of them. So if you start in the beginning, the first decorator class, what it does is it basically decides should there actually be a node based on that function or not. So in more traditional sense, you can think about it as if-else statements. In this case, for example, this would be the previous version without decorators. How you can implement it is you would have an if statement buried in this node. In this DAG, the new DAG, you can see that, for example, you have this config file, and this just tells you that all the nodes that are have a corresponding value are actually present, and all the ones that don't are not. Next one is once you determine that the function is actually supposed to be a yes.
I think it's super informative and it's cool to see it visually, but maybe you could give example of like decorators. Like the previous one was config when, or like the different config family for people familiar. But yeah, just so if you can give example of decorators that use it.
Fair point. I will, for this one and for a couple more, you're going to see it down the line because we're going to refactor the code. But the ones where I'm not, I'll give. For example, node creator is one that I haven't used in the refactoring, but it actually decides, it actually creates a node from the function. So this is in its most basic form. If you have a function, it will create a node for the Hamilton DAG. But if you want to have something more than just a single node, for example, you can have something like a data loader, which is seen here. And it creates an input-output for the Hamilton DAG. Then next you have node injector, and this is prepending a subgraph to a specific node via an argument of that function. And in this case, we can think about something like pre-processing a certain argument of a function. A prime example would be something like pipe input in Hamilton. And what it actually, so here, for example, it prepends to nodes that convert the input for the feature node. Next one is expanding. So if you have a node, it actually expands in several other nodes. This is, we'll see it later, something like extract columns or extract fields. For a traditional standpoint, think about more about a for loop going through and eliminating certain functions that don't do anything but just create nodes. And then we have node transformers. So it appends a complete subgraph on top of a node. But this is different from the expander because it actually processes that node that you're appending to. So think about post-processing a output of an existing node. So in this case, something like pipe output. And the last one is node decorator. This one doesn't have any visual attached to it because it attaches metadata to the node as an object. And what it's really useful for is something like tagging a function and determining ownership within a code, being able to filter out certain nodes, stuff like that. Okay, so now that we have a basic understanding of all the decorator classes that exist, let's go back to this example and actually figure out how this DAG came to be from a decorator perspective. So in the beginning, we are deciding which database we're going to use. So this is an if-else conditional. We're going to use a node resolver. Then we need to expand this into all the different dates. We can do this with a for loop. And for each of these nodes, we need to reuse the same function to convert that date from a string to a date time. In this case, this would be something like post-processing, and then we just combine them. And now we can see that if we write the code with decorators, what happens is we just need the two functions defined to convert the string to a datetime format. But other than that, all the previous functions that we had in the previous DAGs disappear because all of them are basically attached as instructions for the subgraphs that are being transformed. So we still have the original function, and then we are decide here. This is config when, the node resolver that's deciding which region to choose. Then we have extract fields, which is expanding it into 3 different nodes, and then it's the post-processing part. And then we feed them further down the DAG. And now you can see also that when you're using decorators, adding, for example, a new region with a new date format is fairly straightforward because the only thing that changes is effectively adding another conversion function and then adding a new database call plus the corresponding decorators. So this keeps code much cleaner, less verbose, but also increases explicitness, which means you can really track your assets. Parting words. stacking decorators is very fun. I've run into that problem many times, but really start simple and reach for the advanced tools when needed. Even one like thinking about how to do it without decorators first, and then adding when you reach limits that cannot be solved without them or makes it harder. And also, I think that if there's decorators missing or other tools, Hamilton is a very excited community for building stuff. So just reach out.
I think this is a really important slide. Hamilton gives you a whole bunch of tools, and you kind of get to choose how to use the tools in your toolbox. Some of them, and like at some point, if you've been developing in Hamilton for a while, like everything kind of looks like a nail, right? So you're like, oh, like I see this problem, I can solve it with decorators. But then when you show that code to somebody else, they might be like, well, you know, I was excited about the explicit thing, but a Jupyter notebook would make more sense. So it's always a trade-off, right? And the right number of decorators sprinkled in the right place, I think, can get you sort of just along the point in the trade-off curve where it's both explicit and modular, right? And like easy to work with. Too many can be a problem, and then also sort of not using and making it too explicit can be a problem. And I think the idea is we have just sort of the goal is to have just sort of the right set of decorators that you're going to explain how they work to like ensure that you don't end up overdoing it and you don't end up underdoing it. And you have just the tools you need, and they're a building block for you to decide. Hamilton isn't going to tell you the exact perfect way to do it, but it's going to give you enough tools so that you can use it for your use case, because every use case is different. And the higher level stuff should be able to make you move faster while also keeping it sort of nice and explicit and modular. So.
Yeah, to add on that, I think like the example that Jernej gave is telling, because thinking from a testing perspective, it reduces the surface of testing. Like there were fewer functions to care about and make sure they work. Might be harder to engage with like the entire Hamilton framework, but I think it's beneficial over the long term, because you only have the date conversion part, and then you can do tests over like, is my graph well structured? And then you're confident that your pipeline won't break. Whereas the previous one, like, okay, I have 12 nodes and each node has a function, then you have to test the 12 of them to ensure that your system doesn't break. And someone may tweak a single thing in a single place without telling anybody, and you need to keep track of all of these changes. So.
And yeah, to add to that, testing for any sort of machine learning code, anything where you have pandas data frame, pandas series that aren't like very explicitly sort of like rules of how they should work, can get really ugly, and you just don't want to write too many of those. So this is where there's value in that. Obviously, helper functions you can test as well, but you get both sort of the readable graph structure and the unification of functions. That's a nice way to do it. So,
can we add this presentation to the docs, or find a way to make this part of the? Like,
yeah,
I think it was very helpful to see.
This is the secret. When you and I were working on it, there's that beautiful diagram you have on the. I guess I sent you a diagram and then you made it actually look good. But this one here, I'll share it because I'm like super stoked about this. Is like really, really cool. I think this one just tells you exactly how the decorator framework works in a way that makes it so you can actually debug it. What we can do also is like attach this to code. So it's like, okay, like here's, because this is like one function, this is one set of functions, and it's like a nicely way that it's mapped out. And I think this makes it so that I forget how this works every time I like spend more than a month and I haven't touched it, and then I like go back and look at something like this. It's super helpful. So yes, I think we should integrate this back into the docs, and have this presentation and this these slides sort of reference as well.
Yeah, since you're not you're someone who's coming with fresh eyes. So one of the things, the design decisions Elijah and I had always thought about, or at least gone back and forth on, is should decorators have precedence in terms of stacking, or is it based on the life cycle? And you can tell Elijah and I have differing opinions. I don't know. Is there any? Do you have any thoughts there? Yeah, should it be like, should order of the stacking matter, or should people have to understand what the decorator is?
That's an interesting one. I think you need to.
There's obviously what we have today, but then it's like, it's more, was that a challenge or not? I guess.
it does get a certain. You have to get used to it to a certain extent, and then also don't be surprised when you try to stack decorators that don't work together yet. There's that problem as well. So not all decorators can be stacked.
Yeah,
in terms of order, there's an argument for readability that makes a lot of sense, right? If there's a precedence order that's implied, then why should you be able to write it out of order, right? Which means an extra validation set might make sense because we store like all the things. We could actually store the order of all the decorators. That'd be a simple change to make, and then you could validate that the order is correct. And you're like, no, you'd have to switch it. That said, there is nothing. There is a case actually where order does matter, where you have two of the same type of operations, so two pipe output type things. The order of that will matter because one of them will get applied first, and it applies in the order it's done. And then there's a question where order doesn't matter, such that you have two different life cycle stages of the decorator. Like, should that force it to be in the right order? And maybe not. To me, it's like a question of how much we want people to internalize this, or whether we're just so far on this side of the curve that like anybody who's using 3 decorators should really understand how it works, versus most people who use 1 decorator at a time. And this is just like us doing academic arguments. So
I think the most like common challenge I've encountered is like, I would like to decorate the output of an extract or like a parameterized. Let's say I want a pipe output and parameterized, but it's ambiguous. Like, should I write parameterized at the end of my pipe output or before the pipe output? And both could be valid. And that's where I think your solution made the most sense, where there should be an internal order that's respected, and we like lint or parse the DAG and ensure that the way the code is written is the right one.
Yeah. I think I always stack them in order of how I want them executed, which internally corresponded to the lifecycle coincidentally.
Well, because if it didn't correspond to the life cycle, then it wouldn't make, right? Like the life cycle has an order because those are the only graph. Like it's like, okay, go from nothing to 0 or 1, go from 1 to many, go then like add to the inputs. There's like a certain set of things you kind of have to do. But yeah, I think
there's also the part where you said that we're very far on the curve, because when we were talking about this example with Elijah, we were like, are we really going to give 3 decorators? People are going to run away.
I mean, some people really like, right? And you'll find that it's like there's a parallel thing. Like a few people are just really into this and will start writing their code using all decorators. But then when I show new people Hamilton, I try to show them without any decorators, because that can just scare them, right? It's like, oh, another thing I have to learn, versus Hamilton cell is like nothing you have to learn. It's just Python functions and names. So, I mean, I think it's a fascinating architectural conversation too. It's like a lot of this shows how we really like to work with power users who tend to be self-selecting and give us more feedback, and we can work quickly with them. But then there is also a trade back to that, because power users understand how the framework works, and thus we're working on making it more powerful and not making it more usable. I think decorators, for most cases, represent sort of a nice trade-off there. But as we get more and more into the far tail of this, it can get like nuttier and nuttier.
Yeah, in other words, it's like your code.
Yeah. So sorry, I was going to say like the one thing, so you can extend that. So this is where, I don't know yet if you got to the stage, but like you can start to have decorators that create your own decorator that is a combination of decorators. So if you're a platform team and you're watching this and you're like, oh no, there's so many decorators, people get the order wrong, you can always wrap that in a single decorator yourself, but then gets applied.
That's nice, because you bury the complexity inside the platform team, and it could be like just the business thing that you want, and it's fairly complex graph, but you don't have to understand the graph manipulation as much as like, here's the inputs and here's the outputs. And we've seen a lot of people have a lot of success with that. It is a difficult sell to get people to do that, because they're like, wait, because partially it's like the layering of decorators and like creating meta decorators is just like confuses people. But we love it. So cool. All right. I think we should go on to the new features spotlight. So I'll do this, and then you can jump it. Or yeah, I have a notebook.
You take it. You drive it, Elijah.
Yeah. I really appreciate it. There was a point that I want to make.
I was going to say, we didn't say thanks to you.
Thank you. I was going to say thank you. There was a point I want to make where you said at the beginning you jumped into the heart of it. Like, the thing I realized is, had we broken the code in the first contribution you made, I think you might have made like a really small one, but the first big contribution you made, which was the adapter framework, not lifecycle stuff, but not like this, but like the lifecycle adapter framework, not decorators. Had we gotten a bug there, it would have broken literally every pipeline in the whole world, which is probably tens of billions of them. So it's pretty cool that you're able to do that. Didn't have a bug that we have found yet. So fun first presentation. All right. So a little bit, sort of a few new features that we've had since the last one. First, 500,000 Hamilton plus Hamilton downloads. I think it's like 515, 516K today, which is super exciting. That's growing at a steady clip. We also, if you're familiar with Burr, our other framework, have another 500,000, which means we've got 1 million downloads. So super excited about that. Just a nice thing to see how many people, some of those are obviously CI jobs, but like just how quickly it's grown. So, all right. So some recent features and improvements we released. Jernej obviously talked about a few of these. I'll dig in and show code for a few of them, and then we can walk through a notebook for one of them. I'm not going to show everything, although we have docs and everything for this, so it's pretty easy to get started with. Yeah, we got TypedDict support for extract fields, which means that extract fields, kind of as we showed, or was that? It was. I think that was one of the ones you showed earlier. The extract fields. Now you can use a TypedDict, so you don't have to just use sort of a standard dict. We got all the pipe and friends. You showed pipe output, but it's really a whole family of decorators that does the sort of like sequential transformation. So, sorry, we changed. This is me, right? We changed post pipe to pipe output, and we have pipe input and pipe output. Post pipe still exists there, so it was post pipe, and then Jernej took it and made it pipe output, pipe input, mutate. So pipe output takes the output of a node and continually applies transformations, and then sort of changes it so the reference you get for that node is actually the last one, and adds a few intermediate nodes. Pipe input does that same thing, but it applies it to the input argument, right? So it makes it so the node actually points to a transformation of the input rather than the input, and not function of that. Mutate is really cool. It allows you to actually mutate something else in the graph, so you can add sort of these ad hoc transformations later. There's a whole interesting story. Like this is, Jernej did not talk about this, but this actually is, we hit one of the limitations of the decorator framework from an architectural perspective, which is sort of a really interesting point. And you guys can look that up later. Jernej is working on a blog post that we're going to release this week, and I think we get at that a little bit too. We also have in-memory caching. Thierry did this. I'm sorry, I should have said thanks Thierry there, but thanks Thierry for in-memory caching. This is something that was requested by the community. With columns for pandas, polars, lazy frames, all sort of building on top of the Spark version. The cool thing is they use a lot of the same code, so it's not even that much. So you're going to find kind of the right abstraction. And then Ryan from SDAG did the async datadog adapter, which allows you to sort of track Hamilton and datadog in a sort of microservice setting using async. Let's go through a few of these. So with columns allows you to sort of use modular columns inside a subdag operation from elsewhere. So this is basically like if you had subdag and then also made it data frame aware. And I'll walk through this code in just a second. It works for pandas, polars, lazy polars, and PySpark. We got all these docs. So what's happening here, and then I'll walk you through an example too, because I've got a notebook. Is we've defined a sort of module separately. My module here, it's got A, B average. So A comes from the data frame, B comes from the data frame as well. A, B average, and then we got A from the data frame to specify like where the initial data frame, like where it goes to, right? So what's happening is we're saying, okay, this initial data frame we passed into this final data frame is actually this initial data frame with all of these columns here, right? So we want to select all of these, meaning that you apply sort of all of these transformations onto the initial data frame, and then you get a data frame back with those. The name with columns comes from Spark, because Spark has a with columns operation, which is, Spark is nice and immutable. Pandas has assign, polars, I forget what it's called. Jernej figured out all the different ones.
Also with columns.
Also with columns, yeah. So polars took it from Spark, but basically it does sort of this common operation. And the idea is that if you're in feature engineering, it's not always a sort of linear set of map operations. Rather, it's a like you'll do sort of a bunch of map operations, and then you'll do a bunch of joins, and then you'll do a bunch of map operations, and be able to put those map operations into nice sort of modular places and run them inside a DAG, then take it out, do joins, and go back into that sort of like column level operations. Gets you most of the way towards what you want in feature engineering. So let's go through just the simplest example with column pandas is actually in the examples thing. Let's just zoom in. Okay. All right, so this is just a Jupyter notebook. We'll be using the Hamilton extensions here. So we're creating a module here. It has a config. We've got a final output node here. And what we're going to do is we just have a basic sort of CELTA module that's called myfunctions here, right? So we're creating a module called myfunctions, and this is actually the Hamilton Hello World case, except we've added sort of a different config here. I don't think I think the config is not super essential. So what we do here is we're call the with columns on this final df, meaning initial df is initial df with the columns of my function. And we're saying, okay, pass spend and signups from the data frame in, so we can use those because those are inputs in here, right? So this module here is going to function as transformations on the input data frame, taking in the column spend and signups from the initial data frame and doing a bunch of transformations. And when we look at the DAG, it looks something like this. You can see we've got our initial data frame here. Then everything else is prefixed under this final df dot, right? Because we're doing sort of these transformations, and the namespace is final df because that's the name of this. We're going to look at we extract signups, extract spend, then do some manipulations on top of spend and signups, some further manipulations on top of it. And then we get the final one, which is sort of appending it all together. I think this is added by the framework. Yeah, because underscore append is added by the framework here, which adds them all together to form a single one. And then we've got this final the data frame out, right? So all of this stuff is the subdag that's done sort of dynamically created from the other module. If you want to make changes to the columns that this final df has, all you have to do is select another one here, these output columns, and add one here, right? So if we want to, I'm not going to add another one now. Let's add another one now. Define spend standard dev times 2. Let's say we want to double the standard dev, and obviously this is, I should not be doing it live after not practicing, but it'll be fun. Return this guy times 2. So we've rerun that. Now we want to get spend standard deviation times 2. This should both be in the DAG and be in the final one. Of course, I get an error here. That's because I did the, it's supposed to be a series. I'm just going to do, instead of this guy here, I'm going to do unit variance times 2 because I know this one is a series. Because we don't do the float to series combination.
Yeah, it's going to name it different.
Yep.
All right. That was actually a conscious decision to prohibit this, because you never know how to. You don't want to just have a column out of a value when you're not expecting it.
Yeah, I think it's a good one to make it explicit again. And in this case, I'm adding it to here, and let's see, works. All right. So now, if everything worked out, we have doubled it, right? And now we're going to run it, and we can see we've got the spend zero mean unit variance, spend zero mean unit variance double, as well as all the spends and signups from the previous one as well. And again, we've got the graph here too. It also works in async. I need to show it now, but this is sort of the power of what you did is kind of just the right abstraction that allows you to do sort of async operations as well. But yeah, so just to highlight the value of this before we go on to the next few, the idea is you have all of these columns. You can operate, you can change this in whatever way you want. And this can operate separately from the DAG. So you can sort of run tests on just that sub module. You can embed it in the DAG. You can even use it in multiple places with different configurations. We didn't show how to use that, but there's all sorts of ways to reconfigure it. And thus you can have sort of, if you have one sort of more modular set of features, you can reuse it in a bunch of different ways. World Oyster here. So
yeah, I mean, one of the things that allows you to get around is the renaming of columns potentially, or if you have a raw data set, you can then have a transform data set, and they can have, you don't have to expose those columns to Hamilton and run into kind of naming issues. Instead, the with columns can kind of hide some of that because it's all namespaced.
Yep, this all uses the subdag. So And it actually does use subdag under the hood, which is kind of cool. So we try to like reuse a bunch of the components. Okay, in-memory caching. Thierry built this. This is super exciting. You can persist in memory for a quick dev. You can actually then like copy over from your in-memory to another store. So in this case, it's a little bit under like one level under the hood, but in this case, we have sort of a simple in-memory store. I didn't show running it, but we might run it. Then driver will have a cache. The cache will just have a dictionary of the results in memory. And then you can persist to this so that if you reload from it, you can sort of reload from this type of persist to the load from Hamilton cache and get your results again. It's good, yeah, good for local development and sort of quick loading. If you want to be able to cache, say you have expensive operations that you don't want to reload every time, or even really quick operations that you just want to sort of store in memory. Obviously, if you have huge data outputs, you want to be careful here. But if you have smaller data outputs that you don't want to like worry about reading files and you just want to iterate super quickly, this is good, and you can always persist later. This is mostly for development, but I would not be surprised if some people start using it in production, especially because you can persist it. So curious to see where that goes. Async Datadog. This is a fun graph that shows kind of the difference between running. This is so async. So Datadog is a lifecycle adapter, right? And it just creates a span for each node. And so you can sort of visualize how long it takes and attaches some data to it as well, I think. The top one is actually using the synchronous lifecycle Datadog adapter for an asynchronous one. And the trick to know here is that the synchronous one just runs at the beginning and end of every function. And the way that Hamilton works, the end of every function will be after the async function is called, which async functions are always infinite, or always instantaneous if they're correct and they do the true await, meaning that it runs all of the rest there, and then most of the time it's spent waiting for the promises, right? The async Datadog adapter actually does wait for the promises nicely here. So you can see here where it looks like everything's super quick. That's really just the result of calling await, which just like creates a promise. This one is actually the result of waiting on the promise. This one's the result of calling the function that creates the promise. This one is the result of calling the await on top of it, and you can see how it's actually functioning. This is, again, Ryan Witten's example that he posted on the issue there. And sort of the motivating one. He created it, did some clever things to get, again, like getting async and sync to share code is really complicated, but Ryan managed to do some clever things to reduce the surface area. Pretty cool PR if you check it out. Yeah, so that brings us to the end of this. The next meetup will probably be in February at some point. If you're interested in speaking, we can do something like this where you deep dive into something in Hamilton in particular. We let people talk about their use cases. People have talked about libraries they built on top of Hamilton. Really, anything that's sort of interesting to the community, we're happy to entertain. So appreciate all your time. And I really appreciate you going deep here. This is super fun. And nothing like having somebody else go deep who has a fresh eye on this to really understand sort of the limitations of what you built and where to go next. Because like Hamilton, like most software, is kind of like a living, breathing organism. We can make small changes, we can make big changes, and we can like rewrite pieces entirely, and having fresh eyes is extremely important for that. So thank you so much, really appreciate it. I really appreciate all for coming. So
thanks everyone.
Yeah. So if anybody has something they want to say, open mic here, or we can just call it a day and on with it.
Yeah, I'll just wish everyone happy holidays and excited to see how 2025 turns out.
Yeah. Happy holidays, everyone.
Sure.
All right. Cheers.
See you.